Hi, in this lesson, we'll look at equivalent Boolean expressions. In the previous lesson, we learned how to evaluate compound Boolean expressions in our program code. In this example, we have a Boolean expression, cannot ride, that will evaluate to true if the user cannot ride a particular ride. The cannot ride Boolean is being assigned the result of the compound Boolean expression, not tall enough or not old enough. This means that if the user is not tall enough or if they are not old enough, cannot ride will evaluate to true. Let's see this in action. We've initialized tall enough to be equal to true and old enough to false. When used in the compound expression, they hold the same value. Because the not keyword is placed before the variables, the Boolean value of the expressions are flipped. When evaluated, because one of the conditions is true, the expression cannot ride evaluates to true, which means that the user cannot go on the ride because they're not old enough. Interestingly, the expression is not tall enough or is not old enough can actually be written another way. The expression has an equivalent value that is slightly more simplified, is not tall enough and old enough. This equivalency was first discovered by Augustus de Morgan, who was a British mathematician. He devised two rules that can help us evaluate equivalent compound Boolean expressions. De Morgan's laws are rules that show how we can negate ands and ors in compound Boolean expressions. Not A and B is the same as not A or not B. Not A or B is the same as not A and not B. When written out in Java, the expressions are as such. We can use these equivalencies to help simplify Boolean expressions and to express different logical expressions. When looking at these statements, it's not obvious that the statements are equivalent. Let's take a look at how they're actually the same. On the left side, we want to build up the expression not A and B. So we will look at every combination of A and B and see what the result is. The first possible combination for the value of A and B would be true and true. A can be true and B can be false. A can be false and B can be true. Or A and B can both be false. That's every combination possible. Now let's look at what happens with A and B in each case. True and true results in true. True and false is false. False and true is false. False and false is false. To negate this column to fill the column on the right, we just need the opposite of each item. So true, false, false, false becomes false, true, true, true. Now let's do the exact same thing with the right side. First, we'll add all of the possible combinations of true and false to the A and B columns. For column not A, we will just take the opposite of everything in column A. For column not B, we will take the opposite of everything in column B. To get the final column, we just OR the last two columns together. OR is true whenever one of the inputs is true. It's only false when both are false. So when not A is false and not B is false, then not A or not B is false. As we can see, for all of the possible A and B combinations, the result of not A and B and not A or not B are the same. This proves that writing either of these expressions will result in the same evaluation. Now let's use truth tables to confirm the OR statement. As we can see, the evaluation of not A or B is equivalent to that of not A and not B. No matter what the inputs of A and B are, both sides of the statement have equivalent results. We can also visualize De Morgan's laws using a Venn diagram. Imagine the entire gray square as all people everywhere. We can represent all the people who are tall enough to ride the ride by filling in the Venn diagram. This represents all the people who are old enough to ride the ride. If we OR them together, these are all the people who are either tall enough or old enough to ride the ride. And these are all the people who are both tall enough and old enough to ride the ride. How can we represent not tall enough and not old enough? Remember, this is tall enough and old enough. Our goal is the opposite of this or the negation of this. So everything that's green, we will make gray, and everything that's gray, we will make green. This is the opposite. All the people who are not tall enough and old enough to ride the ride. De Morgan's laws say that this previous statement is equal to all the people who are not tall enough or not old enough. Everything in green are all the people who are not tall enough. Now everything in green are all the people who are not old enough. If we want all the people who fit into either of those categories, we need to combine all of the green. This is the group of people who are either not tall enough or not old enough. As we can see, the visualization between both Venn diagrams is the same, indicating they evaluate to the same values. How about when we negate the or expression? According to De Morgan's laws, the expression not tall enough or old enough is equivalent to not tall enough and not old enough. Here we have all people who are tall enough or old enough. To negate that, we would just take the opposite. This is all the people who are not tall enough or old enough. Now let's look at the other equation, not tall enough and not old enough. Let's build the right side of the equation and see what happens. These are all the people who are not tall enough. These are all the people who are not old enough. To and them together, we want all the people who are not tall enough and not old enough, as shown here. So we see that they are equivalent. Both of these statements are true, and we can use De Morgan's laws in our programs. This can help us simplify our Boolean expressions. Let's try a couple of practice problems using De Morgan's laws. Based on his findings, how could we rewrite this expression? This can be written using an or statement. If we negate each statement and change the and to or, we will get an equivalent expression. For additional practice, let's try one more. What is another way we can write this expression using De Morgan's laws? We can change this to an and expression by adding a not keyword before both expressions. Now that you've learned about De Morgan's laws and truth tables for evaluating compound Boolean expressions, let's get some practice in the editor.